just accidentally cleared my work.
11,181. What do you get? 11,181.966.
Units?
Meters per second.
Yes. Is that what you were about to say?
Oh my god, sorry, I did not mean to
Thunder.
say your thunder.
A little over 1,000 meters per second, which is about 25,000 miles an hour. This is the escape speed. If you get an object that manages to go that fast, it will leave Earth and not return, assuming it doesn't hit something along the way. Occasionally this happens. Gas molecules. Because you have light coming in, hitting the gas in the outer layers, it will excite some of it to be going the right speed in the right direction, and that stuff will escape. At the same time, we also pick up dust. So I think there's a net gain in the mass of the Earth over time. All right, so escape speed. Some usually call it escape velocity, but well, I guess ultimately it does have to be going away from the planet. If it goes at a slight angle, then it would have to be more than that to actually escape. So the next question is, suppose there's a maximum speed. Now, trying to figure out what the maximum speed is, Galileo did a test where he was trying to figure out how fast light travels, which ultimately is the maximum speed. And he basically figured reaction time was relatively constant. So he and an assistant got on two hills. The assistant would flash a light, or he would flash a light, probably make the assistant travel. The assistant would see the light, flash his light back, and Galileo would time how long it took. And then he went to a farther distance, did the same thing, and if you take out the reaction time, you should have how fast the light was traveling. And he concluded that if light is not infinitely fast, it's very, very fast. So, not particularly helpful. Eventually, they do come out with an experimental value for the speed of light, which does seem to be an upper limit. And the evidence that it is an upper limit really comes out in 1941. There have been plenty of tests since then. It ultimately comes down to anything that's traveling slower than the speed of light will not pass the speed of light, will not get to the speed of light. Anything that travels faster than the speed of light will also not get to the speed of light. It's a barrier. The only things that can travel the speed of light are massless particles, like a photon.
So 11,000. Sorry.
That is the escape speed for Earth.
That's speed of light or escape speed for Earth?
Escape speed for a man-made object. Now, have we ever achieved this, gotten something going that fast off the surface of the Earth?
Yes.
Maybe.
Yes.
Well, usually we have rockets and
What about that
rockets.
one manhole? That was like.
Yeah, that's what I was thinking of. We don't know how fast it was actually traveling.
Uh,
We have a lower limit because it was in one frame and then disappeared in the next frame. That's what the slow
how did it go that fast? What exactly happened?
Underground nuclear test, I think.
That would make sense.
All right, so if we now assume that there is a maximum speed, and I'm just going to use the traditional letter C for this maximum speed, this is the symbol for speed of light. That squared is equal to 2 big G mass of the planet over our, basically it's the radius of the planet.
Is that a 2 or a question mark?
That is a
Superscript C?
square, that's a 2.
Okay.
So if I want to figure out at what radius would the Earth need to be in order for a light not to be able to get out of it, well, we solve for Rx. Rx is equal to 2 big G mass of the planet over C squared. And so if we're looking for that radius of the Earth, assuming its mass does not change, we get 2 times 6.67 times 10 to the negative 11 times mass of the Earth, 5.98 times 10 to the 24th, divided by 3 times 10 to the 8th, that quantity squared.
And X is just any planet in this case?
Well, this X is for any central body.
In this case, we're using Earth, though?
Yes. That summed it up. So what do we get? And we are working under the assumption that the mass of the Earth does not change, which is probably the most questionable assertion.
Can I use R sub E? Because RX reminds me of prescription.
That's fine. R sub E. Not the Royal RX.
Well, I take a lot of prescriptions, so.
Okay. Try to remember the
10,966,547.2.
Did you square this?
Yes. Yes, I did.
There's something else in this then.
Let me,
I got 0.08863.
0.0. How many zeros?
20.
00.
8863.
Wait, it was 0.00?
Well, it could be 64. Round it.
Or was it 0.0?
I got 0.00.
Oh, okay. Okay.
All right, units.
Racing for a second.
give her a second.
What? Did I say that?
Anyway, just shout out the units.
Meters.
Yeah, it's a distance we found.
Sir.
All right, so what we're saying is that the Earth shrank down. That's the radius. So we got from here to, if I went for the diameter, so twice that, so around there. So if the Earth shrunk down into the size between my two fingers, but lost no mass, it would, light could not, nothing could, basically, you would need to travel the speed of light to barely make it out, and the Earth, in essence, would be a black hole. If they're slightly smaller than that, it would become a black hole. Let's do it one more time, except this time with our sun. What would the diameter of the sun, or radius of the sun, need to be in order for it to become a black hole? Assuming its mass is relatively the same.
Assuming its mass is the same?
Yeah.
I'm sorry, I'm brain blanking. How can it be a different size with the same mass?
Not gonna be a different size, but the same mass?
Yeah.
Denser?
Oh, okay. So size is density included.
Yeah, it's mass divided by volume. So the more mass you have crammed into a smaller space, the denser it is.
So mass is the amount of matter in a thing. Okay. Sometimes I forget that.
All right, so if we're talking about the radius of our sun, we have 2 times, again, the constant 6.67 times 10 to the negative 11th times the mass of our sun, which I have to remember, over 3 times 10 to the 8th, quantity squared. And the mass of our sun, there's no textbook sitting around here.
I have a phone. You want me to look it
Oh,
up?
I have
Please.
a textbook.
Oh, dude,
I mean, I don't.
You will. You want the mass of the sun?
mass of the sun. It's either on the front cover or the back cover. Inside.
What is the mass of the sun?
What
Is the mass of the sun?
I don't think it's there.
Wait, Dr. Fox.
4.4 times 10 to the 30.
4.4 times 10 to the 30th
Well, do you want kilograms or pounds?
kilograms.
Oh, 2 times 10 to the 30.
Stop. Stop. Oh! Guys, I know what the speed of light is. Holy.
All right.
Hey. Yeah. Okay, wait, move your hands.
All right, so, sorry, you're looking for mass of sun?
The mass of the sun is right here. 1.99 times.
10 to the 30th.
Do we want to do
buttoned
one
down.
point 99?
Every textbook I've ever seen, it's either been there or the other one.
So do we want to do 1.99?
Yeah, let's use 1.99.
Okay.
What are we even doing right now? Dr. Fox, is this actually happening? Like, can the sun actually turn into a black hole?
Oh yeah.
Not ours.
Not ours.
We'll talk about that in just a
It'll have to grow a lot, but it's gonna do it eventually.
No, we'll talk about, alright, so.
In,
first,
like,
let's get
billions
the
of
numbers.
years.
And the thing is, if the sun suddenly became a black hole, we wouldn't know about it for
8 minutes.
8.5 minutes. And then we would not know about it at all.
2,949.2.
2,900
49.6222222
units.
meters.
Alright, so it's a little under 3 kilometers. So if the sun, with its current mass, straight down to, I think in essence from Peters Creek to Haynes Mall Boulevard, if it's straight down to that size, it would become a black hole. So let's talk about the likelihood of our sun becoming a black hole. There are two processes going on here. Basically, you have hydrogens that, right now, hydrogens will get together, they will combine, and when they combine, they will create helium.
Are you about to say fission and fusion?
I wasn't gonna use those terms, but yes, this is fusion. So, well, I use it for the periodic table. All right, so anything smaller than or less massive than an iron atom, if they combine, they will produce energy. Anything bigger than iron, in order to create energy, it has to split apart. So the hydrogen bomb, the essence of the hydrogen bomb is you take two hydrogens, smash them together, you create helium, but also the mass of the helium that you create is less than the mass of the two hydrogens combined. And so that loss of mass gets converted into energy using the formula E equals mc squared. If it's greater than, you need a substance that can be split apart somewhat easily. Uranium, the last natural element, uranium can get split apart quite easily, and when it splits apart, the two parts are not have as much mass as the uranium started with, and it, in essence, that loss of mass gets converted into energy. That's the atomic bomb. And again, promoting this idea that all physics leads to weapons. All right, so the sun is losing mass. As it loses mass, it loses gravitational pull, and so try that one again. So the sun has mass, it is pulling in on itself. But this energy that is created is coming out, creating sort of a radiation pressure. And so right now we're in a pretty stable area where the energy that's trying to escape offsets the gravitational pull inwards. As we lose mass, the gravitational pull will lessen and the radiation pressure will be a greater force and the sun will start to expand. So at some point, the sun will be here. It will expand to the point, so we should not get burned up, although sometimes you hear people talk about the fact that eventually the Earth's going to get swallowed by the sun or burned up by the sun, something like that. But as the gravitational pull of the Earth lessens, the Earth is going to be moved. Gravitational pull on the Earth lessens, the Earth is going to be moving farther out. So, it is expected that human beings will long be gone by the time this happens. So we have these two pressures. Now, eventually the radiation pressure is gonna wear out. Because once all the hydrogen gets burned up, and you're now left with smashing two heliums together, not as much energy is created. Some energy is created, but still not as much as when you smash two hydrogens. That's the optimum. If the gravitational pull is strong enough and the radiation pressure is weak enough, it will start to collapse in on itself. If it collapses in on itself quickly, then you'll get a nova or potentially a supernova. If the mass is small enough so that it's never quite enough to pull it back together again, the star is just going to eventually just expand and, well, give it enough time to dissipate. It is expected that our sun is not massive enough that it will collapse in and create a black hole or supernova or nova or anything like that.
That would have to be one of the giants, right?
Yeah, that's my understanding. Now, it amazes me the fact that we can come up with any conclusion, because if you think about it, we are here on this small planet looking out at the entire universe and making conclusions based upon what we see at the moment.
Or a billion years ago, almost.
Yeah.
Depending.
But, you know, we come up with models, we look out, what we see matches the models, we go, okay, we have evidence that this model is valid, and then you make conclusions, write papers, etc. Potentially, well, actually, if the universe keeps expanding, eventually things will get farther and farther away, be harder and harder to see things, and so we just happen to be in a sweet spot where we can still see stuff. Anyway, so our sun is not expected to become a black hole, which would be if it's even more massive and collapses in on itself. If it collapses in on itself, sometimes it'll create enough pressure that it'll then explode, nova, supernova. If it's not enough pressure and there's so much mass there, black hole.
I'd kill for the school to have an astrophysics class.
What's that?
I'd kill for the school to have an astrophysics class.
It has been talked about, I've had students in the past who have sort of wanted something like that. Occasionally they offer astronomy, but that's different.
At least it's not astrology.
That's for the English majors, right?
No, that's for the delusional people.
I think my statement might still stand. All right, questions?
No.
All right, now let's get back to more practical matters. By the way, this formula here that we had, in essence this, but put in the variables. When you get into, in classical physics, gravitational force is this attractive force. When you get into modern physics and general relativity, what's happening is that a mass will warp space and things are just basically trying to travel in a straight line, but because space is warped, to
So
what's
it's like a whirlpool?
Yeah, I think the classic example is, at least if you take a dimension away, put a bowling ball in a trampoline and try to roll something across the trampoline, it will start to spiral. It looks like it's being attracted to the middle, when in fact, it's just the fabric is warped. But the formula still holds. This formula, this right here, S also could stand for Schwarzschild. This is the formula for the Schwarzschild radius.
The what?
Short.
Short steel?
Schwarzschild.
Oh, Schwarzschild.
Do it with a German accent. He was a German physicist. They do this, the Schwarzschild bit.
Yeah, how do you spell his name? Is it just Schwarz and then like shield?
Yeah, it looks like Schwarz and then child.
With an A on the end or not?
No E on the end. So SCHW.
I mean, according to that, it
ARTZ.
would probably have to be like Schwarzschild. Or Schwarzschild.
Quite possible. He's been anglicized.
He's been what?
We've anglicized the pronunciation. Schwarzschild. Say it quickly.
Me? Right now?
No, I mean, as a general rule, just say it quickly and
No.
People know what you're talking about.
Yeah.
Stretch it.
Now you're trying to figure it out.
All right, so I went and talked about the mustard gas attack. They do that bit?
Mustard
I
gas?
did, that was a nod.
Wait, what
Okay.
are you talking about? Mustard gas. You brought it up. I don't.
We're talking
I
about
can't
mustard
story back,
gas?
but-
And like the
Mustard
guy
gas.
who created Zyklon B.
Yeah, that's right, that was this class, okay. Just refer to your notes.
Oh, did I? Oh, I haven't told you about my dad's response to Thomas Cromwell or whatever his name was. Mr. Cromwell.
Oh, after
Yeah.
class. I
He
definitely want to hear his
responded
response.
to that, so I'll show you the text.
All right. Looking at the notes from last week, we basically had something that we had an object falling, so let's do box summary. Yes.
Back to the basics.
Yeah.
I love it.
M stands for mass.
Yes, because ultimately the mass does not matter. Let's start it off from an initial height of,
10 meters.
sure. What could it be? And I want to know how fast is it going at the bottom of the ramp. Now, we can use Newton's second law to do this, and that's perfectly fine. But I want to use energy.
Okay.
So first we'll do it without friction. What are the forces acting on the mass?
Gravity.
What are the forces
Force of
acting on the mass?
Force of gravity?
Thank you.
And then, normal force. And that's all.
Normal force. Conservative or non-conservative?
Non-conservative.
That is correct.
Did you say no one or non?
Non.
Okay.